in this lecture, we're going to be talking about stress and faults. So some of the high-level learning objectives that we're going to be talking about, that stresses occur in the subsurface all over the place. And there's specific types of stresses that are associated with faulting. And faults can also occur in different parts of the world and at different levels of the subsurface. And they typically are related to plate tectonics, not always. And the different types of faults that we're going to be talking about today are transform or strike slip, reverse or thrust, and normal faulting. So what's stress? My Google search is definitely worried about me. I'm not talking about this kind of stress that's imaged here. I'm talking about stress in the subsurface. So let's talk about what those types of stresses are. So stress is a force per unit area, and it's represented by the symbol sigma. And there's lots of different types of stresses. We have anisotropic, we have differential, homogeneous, hydrostatic, lithostatic, normal stress, principal, shear stress. Okay, don't stress too much about this because this is just for your basic knowledge that we have all these different types of stresses, and how these stresses are formed in the subsurface are ways that we describe it, and we can calculate stress. And sigma is definitely used in some higher level math, especially when we start talking about how things change within the subsurface. So stress is the intensity of force. A given force acting on a small area will have a greater intensity than that same force acting on a larger area. So in geology, we can talk about stresses that are applied in 3 dimensions. We have the principal plane of stress, we have the principal axis of stress, and then we have those principal stresses. So if you've taken any higher level math, then maybe this looks familiar to you. Again, don't worry about it too much, but when we talk about the subsurface, we have 3 dimensions. We have the X space, we have the Y space coming in and out of the page, and we have the Z space, and Z describes typically the subsurface. And so when we talk about stresses, we can talk about how stresses are applied on those different faces. And within that, there's different directions of which stress can be applied. So if you read up on different stresses, you might see this figure, and this is called a Mohr diagram. And this diagram is to solve equations for normal stress and shear stress that are acting on a plane within a stressed body. Again, don't worry too much about this. I just wanted to bring it up just in case you're reading through a book or come across an article or read something online about different stresses. So this is a Mohr diagram, and we look at how stresses and failure stresses occur in the subsurface. Okay, so stress is applied to rocks in the subsurface. These rocks can deform or they can slip. Those, like I said, these are the failure envelopes. So if there's too much stress applied, then the rock can deform. And deformation occurs in different directions based on the rock's internal structure and the preferential stress directions. Remember when we talked about rock formations, how certain rocks have striations or foliations. Typically with that comes a preferential stress direction. Stresses found in the subsurface are never uniform. It's never easy. The math is always really hard. We can never model it accurately. And even then, it's quite complex. So if you ever do any subsurface modeling, it's really difficult to understand how much stress a rock has undergone and the direction of stress, because every little piece of a rock can have stress acting on it in a different way than a neighboring rock. When stress is applied on rock and exceeds the fracture gradient, it causes the rocks to break. So this is one of those keywords that some people are really interested in understanding. And maybe if you've read up on this or if you're concerned about it, when we talk about the fracture gradient, it causes the rock to break. This is what we call fracking. And so I'm going to talk a little bit more about this process in the oil and gas lecture later on in this semester. But basically, what you do is the rock is under so much stress that it breaks apart, and that exceeds the fracture gradient. Okay, so that's it about stress. We're gonna relate it to faults here in just a second. So what are faults? Again, different kind of fault. We're gonna talk about geologic faults here. A fault is a crack in the Earth's crust, and they can typically be associated with plate boundaries, but not always. Quick fault movements can cause earthquakes, and slow fault movements can cause creep. So when we talk about, we're going to talk about earthquakes and mass movement in later lectures. But if you think about something moving quickly, that's when you have a release of stress, and that's where you get those earthquakes, those sudden jolts. And if you have slow movement, like the whole hillside that's moving, that's when we get this creep effect. There's three major types of faults: normal, reverse, which is sometimes called thrust, and transform, which is sometimes called strike slip. And there's other types of faults too. These aren't just the only ones. Geologists love to come up with different words to describe different things. We have things like detachment faults, extensional, oblique slip. Like I mentioned, thrust, but there's different even variations of what a thrust fault is. Scissor fault, transfer fault, and transform. So there's all these different types of faults, but we're going to focus on just the three, and those are typically a little bit easier to visualize. First up, a normal fault. A normal fault occurs in areas where rocks are being pulled apart, and this is a tensile force, so that the rock crust of an area is able to take up more space. So the rock on one side of the fault is moved down relative to the rock on the other side of the fault. Normal faults will not make an overhanging ledge. It's likely that you could walk on an exposed area of the fault, and you wouldn't necessarily know it. It might just look like a little slope. Oh, here's a good animation here. We're going to watch this a few times. So here's a normal fault animation. You can see that this down thrown side of the fault is moved down relative to this piece here. So again, this block is moving down. And over time, if this were to, immediately you'd see this difference here, but if this were to fill in with some sediment, it would be difficult to see a normal fault at the surface. Okay, let's look at a reverse fault. A reverse fault happens in areas where rocks are pushed together. This is the compressional force. So that rocky crust of an area must take up less space. Rock on one side of the fault is pushed up relative to the rock on the other side. And one area of the fault is often overhanging, and so you couldn't necessarily walk on it. And thrust faults are a special type of reverse fault which occur when the fault angle is very low. So this angle, let's say that's about 30 degrees. If you had a very low angle reverse fault, like it would be nearly vertical, that would be an example of a thrust fault. So let's look at that animation. Okay, so you can see how this rock is being pushed up relative to that. And if you were to stand right here, you'd be on the overhanging side of that. You'd be on this ledge. Let's look at that again. So now you can see that this piece is now being compressed together, and it overall takes up less space. Here's an example of that thrust, where the angle is a little bit different, and it's not quite as dramatic, but they're being pushed together, being squeezed together. Okay, last is a transform fault. Transform faults happen in areas where rocks are being pushed away relative to each other. This would be a shear force. So this would be movement along a strike slip. Again, transform or strike slip are used interchangeably here. So movement along a strike slip fault is horizontal with the block on the other side of it. So one block is moving into the page, one block is moving out of the page. And strike slip faults do not make cliffs or scarps or hills or anything, because they're basically level to each other. Let's look at an example of that. Okay, so you see that this block is coming towards us, and this block would be moving away. So if you're to be standing at the surface, you'd be standing here at the road, and the road would then look a few feet away from you. Okay, so here are some key words when we use to describe faults. Okay, so in a strike slip fault setting, that would be here. This is considered the strike. That's the direction in which the fault is headed. Yeah. So if north is a certain direction, the direction in which the fault occurs relative to north would be a description of its strike. When we have a normal fault, again, this is where one block is moving downward. This would be an example of the hanging wall. This would be an example of a footwall. And the direction in which that fault occurs in the subsurface, that would be describing the dip. And we also see those same words used in a reverse fault setting as well here on the right. Okay, so I have like a little demo to show you of what it might be like if you're on the edge of a fault.
Between blocks A and B is where we have an example of a normal fault. This is where block A is being moved down relative to block B. Again, in this setting, we would be able to see that there's a difference here in the subsurface layers. If we look at it a little bit more head on here, we can see that this block has just moved ever so slightly down. And we see that there's not as much variation between these two, and this block has actually just only drooped a little bit. If we were to look at the surface here, again, we'd have our little guy. He would be hanging on here at the edge between block A and B in a normal fault. Between blocks B and C is where we see a reverse or a thrust fault. At the surface, you'd be able to tell that there is a little overhang. So here's like my little guy, and he's hanging over on that cliff there. So there's quite a bit of clearance of him sitting on the edge. And if we were to look in the subsurface, you can see that these layers are actually offset by quite a few feet here. If this is the subsurface, this might even be hundreds of feet. So in a reverse fault setting, you would definitely be able to see how this block is being moved up and this block is being moved down, and we see the offset in the subsurface layers. So I'm looking at a strike slip fault between block C and block D. If we look at it from this angle, we can't really see a lot of variation in the subsurface. But we're able to see that fault more clearly from above. So if one block is moving towards me, that's what this arrow indicates, and one block is moving further away, we see the surface characteristic of where, say this is a river or something, the edge of the river is then moved a few feet, a few hundred feet, and we can see the surface characteristic of a strike slip fault.
Now that we've described the three different major fault types, how do we represent faults on a map? So you might be seeing some of this if you're taking the lab portion of this class, or maybe you'll see it on a map, sometimes even just looking in Google Maps, or if you're into hiking, you might see some of these symbols. So this line represents the location of the fault, and the U means the up-thrown side, D means the down-thrown side of the block, and the arrow indicates the direction in which the fault is moving, and that number there is the dip at which the fault is angled at. Thrust faults are usually represented with these little triangle guys, And of course, if we're in a strike slip environment, you would see these arrows that indicate which block is moving which direction relative to the other. Again, this line would be the surface expression of the fault. This will become more important as we talk about topography maps and geologic maps, and you might see these symbols. So here's an example of that. Here's a geologic map, and right here is an example of the up-thrown side and a down-thrown side of the fault. So if we were to look at this in cross-section view, again, that's to take a slice right through this map, we would see that this is where the fault is located. This is the up-thrown side. This is the down-thrown side. And in cross-section view, we can see that these little arrows indicate that this block is moving downward relative to this block right here. If we move a little bit further to the right, if you remember, these little triangle guys represent a thrust fault. So here is where we see that, that thrust fault located right here, and that arrow indicates the direction of that thrust fault. Okay, so now if we were to look over at this other example, here's another geologic map. If we were to look at a cross-section between A and A prime, so between here, A and A prime, we'd see that we'd be crossing this fault. This is the down-thrown side. Here's the up-thrown side. And again, this is where we would see that fault as we cross from left to right. Okay, so like I said, there's a correlation between stress and faults. Compressive forces or compressional stress is where we have things being pushed together, and typically we see that in the shape of folding. So if compressional forces are slow, we get folding. If they're fast, that's where we get a fault. And this is where we get a reverse fault. You can see here that here's my little hanging block there. Okay, in a tensional force setting, this is where we have stretching and thinning. So if it's slow moving, we get this, this stretch, or these are being pulled apart. And that would look like a normal fault. When we have shear forces, that's when the blocks are being moved across from each other. In a slow setting, we get shearing, but in a fast setting, we get a transform or a strike slip fault. In this demo, we're going to be using marshmallows to demonstrate different types of stresses. Okay, so I have a little grid here on my marshmallow, and I'm going to simulate compressional stress, which is pushing the marshmallow together. So you can see how the grid lines then become elongated in the vertical direction. Okay, next is a tensile stress where it's being pulled apart. Again, here's my little grid line. So if I pull it apart, you can see that the grids become elongated in the horizontal direction. And last is shear. This one's a little bit more difficult to simulate. Again, here are my grid lines, and if I apply a shear stress, you can see that they become elongated and disformed in a different way, and they become more diamond shape. That's it for this demo. Hope that's helpful to your understanding of different types of stress. Does this look familiar? Here's a picture of the globe. And we've looked at other pictures like this, but this one is actually where stress and faults occur. And you can see that the Earth is under a lot of stress, and I don't blame it. There's a lot going on right now. So all these different colors correspond to the different types of faulting that we see. So red colors are normal faults. See a lot of that here in the Europe area. Strike slip. This is where we are in California. That's represented by green. And we have thrust faults in blue, or these are also the reverse faults here in blue. Do you see a correlation between plate tectonics and stress? Remember back to where those plates are located. The answer is yes, there's a correlation between stress and plate tectonics. Okay, so let's look at a fault on Google Earth. This is the Great Glen Fault in Scotland. Now, can you see the fault signature? Before I draw it with my mouse, maybe just take a quick second and see if you can identify it. Okay, so I'm going to just move my mouse along that fault. Do you see it here now? Okay, this is where the fault is. So based on this picture, can you guess what type of fault it is? Okay, so if you guessed strike slip, then that's correct. We see strike slip faults most clearly from aerial photography because they give the best surface expression. Other faults are really difficult to identify in the subsurface because we don't always see those layers from a different perspective. So here's a different picture of that. So again, here's exactly where that fault is. This would be a picture from maybe standing right here looking down that fault line. And the block on the left is moving north relative to the block on the right. So is this fault active? Well, there's been about 3 to 4 magnitude earthquakes that have occurred in the last century, with the last earthquake in the 1900s. So I'd say, yeah, it's still relatively active. And there's even small tremors that occur in this area. And fun fact that the small tremors right here are usually paired with the sightings of the Loch Ness Monster. Well, here's another famous fault here on Google Earth. Here's an aerial photo of the San Andreas Fault. So can you see where that fault line is? Well, it's right here. And like I said, strike slip faults are the easiest ones to see on Google Earth because we see the surface expression. And here you can clearly see that this is the creek bed on the left, and it has been displaced quite a bit. Here's the creek bed on the right. So it has moved relative to this fault. Here's another picture of the San Andreas. It's fairly active with earthquakes pretty often. We see a lot of other earthquakes that are associated with San Andreas, and it's under a lot of stress all the time. The last major earthquake was in 1906 in San Francisco, but there's been a lot of studies done, and of course they say that we're overdue. So I can't wait to talk to you more about earthquakes in the next lecture. So what did we learn today? We learned that stresses are typically associated with faulting. We see shear compressional and tensile stress that are associated with strike slip, normal, and reverse faults. So faults can occur in different parts of the world, and they're often related to plate tectonics. There's many different types of faults, but the 3 that we focused on are transform or strike slip, reverse or thrust, and normal faulting. That's it for this one. See you later.